Record. Hello, Math 6B students. Welcome to another video. Today we are going to start talking about convergence tests. We're going to do a couple of them. And before I do that, I wanted to give you an overview of what convergence tests are all about. So our goal when using a convergence test is that we're given some infinite series and we want to determine whether it converges or diverges. Now, why do we want to do this? Well, this is a preliminary task, basically. If we're given the task of adding up an infinite number of numbers, we want to know ahead of time whether the result will be a number, because if it diverges, we don't really want to waste our time adding up a bunch of numbers that don't add up to anything. And if the series converges, then we can be sure that if we add up some of the numbers, then we will get an estimate for the value of the sum. So we might not be able to figure out exactly what it converges to, but we can get as close as we please by just adding up, say, the first 10,000 terms or however many it takes to get within our desired error. So if you recall, the definition of convergence of an infinite series is if you take the nth partial sum and let n approach infinity, if you get a number, the series converges. If you don't get a number, then the series diverges. So that's the IFF there is the if and only if. And so all of the convergence tests that we go over are equivalent to this definition. When you're using them, you're not directly looking at this definition, but if you see proofs of these things in the lecture, then they all boil down to determining whether this limit exists. Okay, so I wanted to go over a couple of examples. So let's go over the first one, the test for divergence. What is this? So this is going to be your preliminary test for this question. Does the series converge? The way I think about this one is that it's a weeder test. It weeds out all the series that quote unquote obviously diverge. Okay, this word obviously is generally not cool to use in a math class because what's obvious to one person isn't necessarily obvious to the next, but I'm hoping that by the end of this, this will seem obvious. All right, so how it works, if the limit of the numbers in the series is not 0, then the series diverges. Okay, so, and if the limit is 0 of the numbers in the series, then your series may or may not converge. Further testing is required. So, what does that mean? In plain English, if the numbers I'm adding up don't get close to 0 as n gets big, then there's no way I'll get a number when I add all of them up. Okay, so I'm not going to prove this. If you would like to see a proof of this, you can ask me in my Zoom drop-in hours, I suppose. All right, so here's some examples using this. Determine if the following series converge or diverge. Now, of course, if we're using this test for divergence here, we don't have a way to show that it converges. The possible answers to this question are it diverges or it may or may not converge. So we can't get a yes answer out of this. Yes, it converges. So if we look at this first one, well, this first one, the limit as n goes from 1 to infinity. According to our test here, we just have to do the limit as n approaches infinity of the numbers in the series and see whether or not we get 0. So let's see here. Well, what is the limit as n approaches infinity of the numbers in this series? So n over n plus 1. All right, hopefully that's a nice easy limit to do. Everybody can tell that that's 1. 1 is not the same thing as 0, so the series diverges. All right, see, easy peasy. What about this second series? Well, if I do 1 over natural log of n, if I do the same thing, the limit is, why is my thing doing this? All right. So if I do the same thing, the limit as n approaches infinity of 1 over natural log of n. Well, we know from before that the natural log of n approaches infinity, so 1 over infinity is 0. So this limit is 0. So what does that mean? That means the series may or may not converge. And further testing is required. This is a phrase you do not want to hear from your mechanic or your doctor. Okay, so that's the test for divergence. It's pretty easy to use, but unfortunately you can only tell whether a series diverges if you're using this thing. You can't tell if a series converges using this thing. So what's another test that we can use maybe to actually see whether certain series converge? Well, there's the next one on the list, which is the integral test. And a rough guide to when you might want to use the integral test is you use this test when the expression inside the sum looks like something you might be able to integrate. Okay, so how does this work? Well, if you have some function that's continuous and it's decreasing, a way to test to see whether a function is decreasing is just by, well, if f prime of x, if the derivative is negative on for values of x greater than or equal to 1. Now, if the sum starts at, say, like 2 or something like that, then we can say, oh, x is greater than or equal to 2 or whatever. So, and another condition on this f of x is that it approaches 0 as x approaches infinity, so it asymptotes off at 0. Now, if this wasn't true, we'd automatically know that the sum would diverge anyway from the test for divergence. So if f of x has all of these properties, it's continuous, it's decreasing on the interval 1 to infinity, and it approaches 0, then the integral from 1 to infinity of f of x and the sum as n goes from 1 to infinity of f of n, both the integral and the sum either converge or diverge. So you can basically pretend that the sum is an integral and then determine whether the integral converges. All right, so what are some examples of this? So the first one is the so-called harmonic series. So this is a famous series. You know a series is important if they give it a fancy name. So the harmonic series has a fancy name. It's an important series that lots of people care about. So this harmonic series, well, let's see here. So the function here would be 1 over n, or I guess if we replaced it with x. So our function is f of x is 1 over x. And you can tell that this function is positive, decreasing, and it approaches 0, right? So, okay, cool. So then, so this function is, so this is positive and decreasing towards 0. I'm not going to go through all of the fancy tests. So that means we can use the integral test. By the way, it's continuous. So this is important if x is 1 or bigger. So if x is greater than or equal to 1. Okay, so that means to determine whether this converges, we just do the integral instead. So we just take a look at 1 to infinity, 1 over x dx. This is log of x from 1 to infinity. All right, technically I should be putting some limits here and blah, 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 blah. But yeah, so this is log of infinity minus log of 1, which is infinity. So that means that the harmonic series diverges. All right, so since I'm running out of room here, I will, for number 2 here, I'll just scroll down here. So a similar series, the sum of the reciprocals of the squares. So if we're looking at that one, so n goes from 1 to infinity of 1 over n squared. So again, we sort of want to look at the function, our f of x would be 1 over x squared. And yeah, this function is continuous. This is positive, continuous, and decreasing towards 0. For x greater than or equal to 1. The reason for the continuous condition here is basically the function has to be continuous in order for the integral to make sense, right? Like integral is something you do to a continuous function. Okay, so that matches that. So then basically we can do the integral and see what happens. So we can see, well, what's the integral from 1 to infinity of 1 over x squared dx? Well, all right, so this is x to the negative 2. So you just do the antiderivative. So that would be minus 1 over x. And then we're going to evaluate that from 1 to infinity. And for plug in infinity, quote plug in infinity, do the limit as x approaches infinity, that's 0. And then minus, when I plug in 1, I get negative 1. And so I get 1. Okay, so this is a number, which means that the integral converges. So converges. Because 1 is in fact a number. This 1 does exist. This exists. All right, which means the integral converges. Yeah, this isn't philosophy class. We can, we don't have to spend a whole bunch of time debating whether 1 exists or not. Okay, cool. So now I should note that the value of the sum is not the same thing as the value of the integral. So important note. The value of the sum as n goes from 1 to infinity of 1 over n squared is not the same thing as the value of the integral 1 to infinity 1 over x squared dx. It's just the fact that we got a number for the integral means that we would get a number for this sum. And in fact, I can prove this to you very quickly. So here's a quick proof. Remember, we got 1 for the integral. I could very quickly convince you that we will not get 1 for the sum. How? Well, this is right out of our first few terms. So n goes from 1 to infinity of 1 over n squared. If I write out the first few terms, that's 1 plus, oh, I'm going to get something bigger than 1 because I'm going to keep adding stuff to this. 1 plus 4th plus a 9th. All right. And in fact, if anybody wants a big mystery to keep them up at nights, you would never guess what this adds up to. This is something that in the course of history basically confounded a lot of really smart mathematicians, much smarter than me. But eventually this guy Euler, who you may know from some of your other classes, figured out that, so Euler figured out that this adds up to pi squared over 6. This is not at all obvious, and I'm leaving this sort of as a mystery for you, but because as of right now, you don't have the tools to figure this out. But if you're really clever, you might be able to figure this out. So what did we find out here? Well, 1 over n squared. If we add up all of those, the sums of the reciprocals of all the square numbers, that converges. And all this integral test really tells you is that it converges to some number. And so if we want to estimate the value of this sum, then we can add up lots and lots and lots of terms. And the more terms we add up, the more accurate our estimate will be. All right, so this third one here, so this is one where we really can get into the, maybe this is about as hard as one of these integrals will probably be, 1 over n natural log of n. And notice I'm starting from 2 to infinity. That's no big deal. We could just move the start of the integral over to 2. So for our third one, the sum as n goes from 1 to infinity, 2 to infinity, 1 over n times the natural log of n. Okay, so again, we're going to look at our function here. Our f of x is 1 over x log x. The reason I started at 2 is just because, well, the natural log of 1 is 0. And so, well, if the natural log of 1 is 0, then I can't plug in x equals 1 into here. But if x is 2 or bigger, this is continuous and decreasing. So if x is greater than or equal to 2, this function is continuous, decreasing towards 0. And you can verify that this limit is 0. So the terms of the series approach 0. So, you wouldn't be able to tell from this. So this means that the integral test can potentially apply. So we just want to see if the integral, this time, because we started at 2, so we want to see if the integral from 2 to infinity of 1 over x log x dx, we want to see whether we get a number for this. Okay, if we do, it converges. If we don't, it diverges. All right, this is one of those dealies where it's probably useful to do a substitution. So if we do a substitution, say u equals natural log of x, du would be 1 over x dx. This seems to be the obvious substitution. Why? Because, well, there's u, and that, and that, and the 1, I guess, like forms du. Okay, so when we make this substitution, we get the integral of 1 over u du, and then we integrate that, and we get natural log of u. I guess technically natural log absolute value u, but whatever. And then we back substitute. The u is really natural log of x, so we get natural log of the natural log, or log x. And then we're going to evaluate this from x equals 2 to x equals infinity. Okay, so, and again, I'm being rather imprecise here, where I should put 2 to t and let t approach infinity or whatever, but I'm just trying to get this done relatively quickly. So this is the log of infinity minus the log of 2. Well, the log of infinity, well, the log of infinity is infinity, and the log of that would be infinity. So this is infinity minus log 2. And so it's infinity minus some number, so it's infinity. Okay, so what does that mean? Well, the area under this curve from 2 to infinity is, in fact, infinity. So that means that the integral diverges, which means the series diverges. So the series sum as n goes from 2 to infinity of 1 over n natural log of n diverges. For future reference, this is an interesting example of a series that the denominators grow faster than it does in the harmonic series, but it still diverges. So, if I go back up to our questions here, this one, 1 over n log n, that diverges. All right, and I have for you guys a challenge question, which is going to be important to just sort of memorize the answer to later on, but you can use this integral test to determine the convergence of the so-called p-series. And we did 2 specific examples of p-series up here. We did the harmonic series, and we did the 1 over n squared series. So the harmonic series was if p was equal to 1, and the 1 over n squared was if p was equal to 2. And what you can do using the integral test is you could show that if p is strictly greater than 1, so if p is, say, 1.00000001, that would converge, and it would diverge if p is less than or equal to 1. We already know it diverges if p is equal to 1, so you just have to show that it diverges if p is less than that. If you're using the integral test for this, note that if p is less than or equal to 0, the integral test doesn't apply. Why doesn't it apply? Well, if p is negative, or if it's 0 for that matter, then the terms don't approach 0, so that violates one of the conditions of the integral test. However, since that since the terms wouldn't approach 0, you'd automatically know that the series diverges from the first test, the test for divergence. Okay, so next time we will go over the two comparison tests. There's the regular comparison test and the limit comparison test, and sort of work out the mechanics of that. And the solution to this challenge question, well, it's a show that problem, so I already gave you the answer to it, so you just have to show that this is true. So we're going to use the solution to number 4 here of the so-called P series. So all of this is called the P series. And that's going to be the basis for our comparison tests. So stay tuned for that, and I will see you next time.